The first half of 1966 saw additional office and laboratory space added to support Manned Spacecraft Center mission objectives. Beneficial occupancy was achieved in the 7-story project engineering facility, the office addition to the Life Systems Laboratory, and the Lunar Mission and Space Exploration Facility. Specialized test facilities became operational. In the 120-foot vacuum chamber, formal test operations were inaugurated with the emplacement of the first flight article Apollo spacecraft to be delivered to MSC. The flight article will be used in both manned and unmanned tests to determine the Apollo spacecraft's thermal responses and habitability in a simulated space environment. In the Flight Acceleration Building, the 50-foot arm centrifuge became operational. It successfully passed its first manned test on May 10th. The gondola can be spun at speeds imposing up to 30 times the force of gravity. In May, a specially instrumented ground test model of the Lunar Module Adapter section was delivered to MSC. The adapter was moved to Building 49, where it was installed in the 105-foot acoustical test tower. Preliminary acoustical tests, started late in the reporting period, will lead to the first full-scale spacecraft structural tests to be conducted at MSC. On the MSC Boresight range, Building 18 was completed in time to receive a full-scale mock-up of the Lunar Module Ascent stage. A movable mount will position the stage for tests of the module's rendezvous radar. In nearby Building 14, the anechoic chamber swing arm positioner was readied for its first operational use. A space-suited subject, wearing a portable life support backpack, was prepared for pattern measurement studies of the backpack's communications antenna. The antenna will supply the voice and data link between an astronaut on the lunar surface and the Apollo spacecraft. The foam pyramids covering the chamber walls absorb stray radiation, eliminating electronic echoes which might distort the test results. A facilities mock-up of the lunar module cabin configuration was used in interface tests with the latest Apollo lunar spacesuit components. A space-suited subject displayed mock-up hardware for the Apollo Lunar Surface Experiments package, known as ALSEP. Bendix Corporation, Ann Arbor, Michigan, is developing the experiments package, which will consist of 7 types of experiments divided into 2 arrays. The astronauts will deploy the equipment and leave it on the lunar surface, where it will continue to record and transmit scientific data back to Earth. The Apollo spacesuits were tested to determine if they had the mobility range necessary to handle the ALSEP equipment. Both the soft suit and the Apollo hard suit proved to have the mobility characteristics needed to perform the required tasks. The aluminum and fiberglass hard suit was also used in compatibility studies with proposed lunar surface survey vehicles. This is a Boeing design, and this is a Bendix design. Such a vehicle to be used with the hard suit is proposed for advanced Apollo missions involving prolonged lunar surface stays. Vehicle investigations are being conducted by NASA's Marshall Space Flight Center as part of the Apollo Applications Program. Long-range planning was also evident in continuing MSC investigations into spacecraft landing systems. A scale model Apollo spacecraft, fitted with nitrogen gas jets, was used in landing attenuation studies. The water tank tests were expanded to include full-scale boilerplate drop tests, using solid propellant rockets to supply the braking force. Test results were better than predicted. The system also represents a significant advance in developing a spacecraft land landing capability. A land landing system would be used in conjunction with a steerable parachute, several designs of which are under development at the Manned Spacecraft Center. The rocket landing and steerable parachute systems are being developed for possible Apollo or advanced Apollo application. Spacecraft recovery systems continued to come under the scrutiny of MSC engineers. Deployment techniques for an Apollo righting bag system were tested both in a tank and in the Gulf of Mexico. The system, which will be operational on Apollo spacecraft, passed its Block 1 qualification tests in May. The ranks of Apollo astronauts were increased to 50 with the addition of 19 new astronaut trainees. This was the fifth and largest space pilot selection made by NASA. The group began classroom and field studies, including geology trips to the Big Bend area of Texas and the Grand Canyon in Arizona. The fourth group of astronaut trainees, selected for scientific backgrounds rather than flight experience, continued flight training at Williams Air Force Base, Arizona. While the men will perform primarily as scientists, they must have a basic understanding of flight dynamics in order to qualify as Apollo crewmen. The crew for the first Block 1 manned Apollo mission was announced in March. The prime crew will consist of Virgil Grissom, Edward White, and Roger Chaffee. The experience necessary to ensure the success of the upcoming Apollo missions continued to accrue in the Gemini program. On March 16th, Gemini 8 astronauts, Neil Armstrong and David Scott, waited out the launch of their Agena target vehicle. The Agena was placed into a near-perfect circular orbit. The countdown on the Gemini Titan II continued as the Agena approached its first pass over Cape Kennedy. At 11:41 a.m. Eastern Standard Time, Gemini 8 rose from Launch Complex 19. The spacecraft was injected into orbit some 6 minutes later. The coordinated launches of the Atlas Agena and the Gemini Titan were termed the most near-perfect yet achieved. The day, March 16th, was doubly significant, for it marked the 40th anniversary of the launching of the first liquid-fueled rocket by Dr. Robert Goddard. 5 hours later, after several altitude and plane changes, Command Pilot Armstrong reported that he had rendezvoused with the Agena. Docking was achieved smoothly. The vehicles remained docked in a stable configuration for 27 minutes. As the crew prepared to perform the first powered maneuvers with the Agena in a linked mode, a violent roll and yaw motion developed. Command Pilot Armstrong disengaged the Agena. To re-establish control of the spacecraft, the command pilot was forced to fire his re-entry thrusters. By mission rules, this meant an automatic early termination of the flight. Re-entry occurred approximately 11 hours after liftoff and placed the spacecraft in a predetermined emergency recovery area some 500 miles east of Okinawa. The spacecraft landed within 3 miles of the aiming point and within sight of a recovery force aircraft. The crew and spacecraft were recovered by the destroyer Mason. Subsequent investigations determined that the violent roll and yaw reaction was caused by the spacecraft's number 8 yaw thruster short-circuiting in the open position. While several experiments were not completed and will have to be rescheduled on later missions, Gemini 8 achieved its primary goal, the first dock in space. It was a significant step in perfecting an operational Apollo capability. The next Gemini mission, Gemini 9, was scheduled for mid-May. Primary mission objectives included rendezvous and docking with an Agena target vehicle and extensive extravehicular activity with an experimental astronaut maneuvering unit. The flight crew were Thomas Stafford, command pilot, and Eugene Cernan, pilot. The 3-day mission was postponed May 17th, but an Atlas engine malfunction sent the launch vehicle into a hard-over position, resulting in the loss of the Agena. A substitute target vehicle called the Augmented Target Docking Adapter, or ATDA, was pressed into service. It was successfully launched and achieved orbit on June 1st. Gemini 9 was poised to follow, but a faulty computer data link delayed the launch 2 additional days. Liftoff of Gemini 9A, as the mission was now called, was at 9:39 a.m. Eastern Standard Time, June 3rd. The docking portion of the mission was canceled when visual inspection of the ATDA confirmed telemetry reports that the docking adapter shroud had not completely separated. Several different rendezvous methods with the ATDA were undertaken and successfully completed. Extravehicular activities performed by astronaut Cernan lasted 2 hours and 10 minutes. This portion of the mission was discontinued when the strenuous work of preparing the astronaut maneuvering unit built up an unexpectedly large volume of perspiration and moisture within the pressure suit. Resulting fogging of the helmet visor forced cancellation of the maneuvering unit experiment. On the 3rd morning of the mission, the flight crew initiated retrofire and re-entry, illustrated here by film shot by the flight crew as they descended through the Earth's atmosphere. Re-entry was so precise that the spacecraft landed within 3,000 yards of the predicted impact point and within sight of the recovery vessel, the carrier Wasp, standing by in the Atlantic recovery area. While approximately 50% of Gemini 9A's mission objectives were not completed, the mission scored several noteworthy successes. It achieved rendezvous by 3 different techniques. It produced more knowledge about man's ability to work outside a spacecraft. And it accomplished re-entry with greater precision than had ever before been demonstrated. Major objectives of the 3 remaining Gemini missions will be to perfect operational techniques for the Apollo program. Gemini 10 crew members, Command Pilot John Young and Pilot Michael Collins, were in training for a launch in mid-July. The Gemini 11 prime crew will be Command Pilot Charles Conrad and Pilot Richard Gordon, shown during a dry run of a photographic experiment at the McDonnell plant in St. Louis. The final Gemini mission, Gemini 12, will be flown by Command Pilot James Lovell and Pilot Edwin Aldrin. Astronaut Aldrin will use the 166-pound Air Force Astronaut Maneuvering Unit, or AMU, shown here during a press conference demonstration. The unit was originally scheduled for use on the Gemini 9A mission. A key element in the success of the remaining Gemini missions is the Agena primary propulsion engine, manufactured by Bell Aerosystems, Niagara Falls, New York. An engine malfunction canceled the first rendezvous attempt during the Gemini 6 mission in October 1965. Engine design modifications were made and successfully tested at the Air Force's Arnold Engineering Development Center, Tullahoma, Tennessee. The modifications were incorporated in the remaining Agena engines. The Agena for the Gemini 10 mission was given a thorough checkout before being shipped to the Cape in early summer. Checkout events also continued on schedule for the Gemini launch vehicles. At the Martin, Baltimore plant, the launch vehicle for Gemini 11 was erected in the vertical test stand. GLV-10, shown in the adjacent stand, completed checkout and was delivered to the Cape in May. While operational techniques were being perfected in the Gemini missions, hardware testing and manufacturing continued in the Apollo program. At the Kennedy Space Center's Launch Complex 34, preparations were underway for Apollo Saturn Mission 201, the first launch of a Flight Article Apollo spacecraft and an uprated Saturn I launch vehicle. At 11:12 a.m. Eastern Standard Time, February 26th, unmanned Apollo spacecraft 009 was launched on a 5,000-mile ballistic trajectory down the Atlantic test range. Staging occurred approximately 2.5 minutes after launch. The 200,000-pound thrust second stage engine ignited and propelled the spacecraft to a 310-mile altitude. This was the separation action recorded by an onboard camera. The command module landed approximately 40 minutes later. Recovery was performed by crews aboard the carrier Boxer. Mission objectives included subjecting the command module's heat shield to high heat transfer rates. 2 burns of the service propulsion subsystem accelerated the re-entry of the spacecraft so that heating rates approached the values that will be encountered for lunar mission entries. Fluctuations in the service propulsion engine's performance degraded the entry velocity, resulting in lower surface temperatures than planned. However, data protractions verified that the current heat shield design is able to withstand an atmospheric entry from an orbital mission. The successful completion of the first Apollo-Saturn mission was one of the most important accomplishments to date in the development of a manned lunar mission capability. The second Apollo-Saturn mission will be flown with unmanned spacecraft O-11. The spacecraft entered final systems checkout at Cape Kennedy in preparation for mating to its uprated Saturn I launch vehicle early in the next reporting period. At the North American plant in Downey, California, the modules for spacecraft O-12 neared completion of integrated systems testing. Spacecraft O-14 had its crew compartment heat shield installed prior to stacking of the command and service modules for combined systems tests. The spacecraft is slated for the second manned Apollo-Saturn mission. The command module for spacecraft 103, the first spacecraft to be available for a lunar mission, completed inner crew compartment welding and was in the final stages of reinforcement panel bonding. Manufacturing progress was matched by activity in Apollo subsystems development. North American conducted a manned altitude test of the Apollo Environmental Control subsystem. The test subjects were sealed in a command module test cell for 14 days, the duration of a lunar mission, and subjected to simulated altitudes they would encounter on such a trip. Closed-circuit television cameras kept a constant surveillance on the test subjects. Blood samples were taken periodically and passed by means of an airlock to medical personnel who monitored the subject's physiological responses. The test included evaluating overall ECS performance during normal and emergency modes, performing toxic gas studies, checking crew system interfaces with respect to lighting and personnel comfort, and conducting microbiological control studies. The test demonstrated that both man and the ECS subsystem can meet the rigors of a 14-day Apollo mission. Other subsystem development efforts included the final test of the Apollo Launch Escape subsystem at the Army's White Sands Missile Range, New Mexico. Nearing abort altitude, the Little Joe 2 launch vehicle was directed to execute a pitch-up maneuver which imposed the most severe dynamic stresses anticipated for Apollo. The launch escape motor ignited and sped the command module free of the launch vehicle. Canards deployed on schedule and oriented the command module blunt end forward, the best position for parachute deployment. All systems performed as programmed. The test qualified the launch escape subsystem for all manned Apollo flights. In the area of lunar module activity, Grumman Aircraft passed a number of manufacturing and development milestones at their Bethpage, New York facility. The ascent stage for the first flight article lunar module completed tank and line installation and was moved to cold flow testing. The ascent stage for the second flight article lunar module was placed in a rotating and cleaning fixture prior to systems installation. The fixture is designed to dislodge metal chips, dirt, and other debris and permit vacuuming at several positions. Lunar module development spacecraft were subjected to continued environmental testing. A test spacecraft covered with electrical heater ribbons was placed in a chamber for thermal and vacuum tests in a simulated space environment. Test objectives included determining the heat load handling characteristics of the spacecraft's environmental control subsystem. Lunar module structural performance characteristics were investigated with the aid of a hydrostatic test tank and a pressurized ascent stage. The tank was filled with water, and the stage was monitored for leaks and other evidences of structural failure. In lunar module subsystems, manufacturing proceeded on the first production models of the reaction control engine units. The Marquardt Corporation, Van Nuys, California, delivered the subsystem for the first flight article lunar module in April. TRW Systems continued development testing of the lunar module descent engine in the company's high-altitude test stand, San Juan Capistrano. Qualification testing was due to start in July. Other altitude firings of the descent engine were conducted at NASA's White Sands Test Facility, New Mexico. The firings marked the first use of the descent engine with a propulsion subsystem. In May, the first propulsion descent stage was removed and replaced by propulsion descent stage number 2, containing more advanced flight-type hardware. A descent engine will be installed, and the stage will be ready for altitude firings later in the summer. Propulsion ascent stage number 1 was also delivered to White Sands. It was installed in the facility's second altitude chamber. Firings are scheduled to start in August. While MSC is responsible for manned spacecraft programs, it draws on the services of other NASA centers and government agencies to aid the accomplishment of these programs. At the Kennedy Space Center, for example, ground crews completed mating of the Apollo Saturn V facilities checkout vehicle. The structure will be used to verify launch facilities, train launch crews, and develop test and checkout procedures at Launch Complex 39. On May 25th, a crawler transporter, positioned under the checkout vehicle and its mobile launcher, began moving the towering load through the 456-foot high doorway of the vehicle assembly building. Its destination was Launch Pad A, 3 miles distant. Total weight of the launch vehicle, mobile launcher, and transporter was approximately 18 million pounds. For almost 10 hours, the Apollo Saturn V moved over the specially constructed crawlerway at speeds up to 1 mile per hour. The most critical part of the trip was the 5% climb to the top of the launch pad. The transporter's hydraulic leveling system maintained correct positioning throughout the climb. The emplacement of the launcher and checkout vehicle verified the mobile operations concept at Launch Complex 39. The event registered another major milestone in keeping the United States lunar timetable on schedule. Information valuable to lunar mission planning is being provided by the Surveyor program, managed by NASA's Jet Propulsion Laboratory, Pasadena, California. The first flight article Surveyor was delivered to Cape Kennedy in March. Following several weeks of pre-flight checkout, the spacecraft was mated to its Atlas Centaur launch vehicle. Launch occurred on May 30th. The spacecraft soft landed on the moon June 2nd. It transmitted over 10,000 pictures, including the first color photographs to be taken of the lunar surface. The Surveyor showed that while scattered boulders could pose a landing hazard, the particular area of the moon was suitable for an Apollo landing. Worldwide tracking facilities for Apollo missions will be handled by NASA's Goddard Space Flight Center, Greenbelt, Maryland. One of the newest Apollo tracking stations neared completion at Carnarvon, Australia. Goddard will also operate the Apollo Worldwide Communications Network. Typical of new construction to meet the demands of the program was this 85-foot relay antenna being built at Canberra, Australia. Similar 85-foot antennas are also being constructed at Goldstone, California, and Madrid, Spain. In support of manned spacecraft activities, NASA's Ames Research Center, Moffett Field, California, has undertaken a broad range of biological studies relative to man's ability to survive in a space environment. In the center's laboratories, animals are exposed to a variety of controlled atmospheres to determine their physiological reactions. Ames is also in charge of a frog egg experiment that will be carried on the Gemini 12 mission. Purpose of the experiment will be to determine the effect of weightlessness on cell development. Frog eggs are used since no matter how they are turned, they always return to a same side up position with respect to gravity. How fertilized eggs will develop in space where there is no up is a question of concern to biologists. Animal studies, funded by the Manned Spacecraft Center, are also being conducted by the Air Force's Aeromedical Research Laboratory, Holloman Air Force Base, New Mexico. Chimpanzees are placed in an altitude chamber and subjected to explosive decompressions. The primates have survived 3.5 minutes in a vacuum with no undesirable after effects. The studies are providing data that can be extrapolated to the treatment of human subjects who may become involved in altitude chamber training accidents. Throughout the first half of 1966, the tempo and complexity of operations increased in all manned spacecraft operations. In the Pathfinder missions of Gemini and in the follow-on programs of Apollo, this nation continued to take longer strides toward achieving its goal of an operational manned spaceflight capability.